in the Mañez paper, but in the compass case. Okay? But the more interesting for me in this lecture is suppose that it's possible to find some constant or contraction exactly equal to exponential or minus c, where the theorem says, in this case, the manifold is not any manifold. The manifold is an homogeneous space or some manifold or negative curvature. In fact, constant negative curvature. The curvature is exactly this number minus c squared. Okay? Any question? One minute for load the result. Google. Infinity volume, this result is not true. No, I have some contra example for this infinity volume. It's possible to make some perturbation in the hyperbolic this point ahead this, close to the zero, and geodesic go to infinity. Any geodesic go to the boundary, but we have this property here, but the volume is infinitely, right? It's as a consequence of the theory. It's exactly your answer of this question, because in this inequality here, suppose that we have some manifold, not necessarily compact, but the manifold has no positive curvature, no negative curvature. Okay, this implies this constant here is very close to zero, and this inequality here implies the lambda is equal or bigger than 1. It's implied in the when we have no negative curvature, it's a contradiction because lambda is a number in 0, 1. Right? In other words, manifold of no negative curvature, the geodesic flow is never an anosov flow. But in the compass case, it's a result of Everline, because Everline says when the geodesic flow is an anosov flow, always appear points of negative curvature. It's a compass case or compact homogeneous space, and a special case, not necessarily any complete manifold. Okay? But more stronger result about the proof of the theorem is if we consider some special geodesics. Geodesics had asymptotic non-negative curvature. It's a geodesic that in some moment the curvature is non-negative. In this case, some geodesic, one geodesic, not necessarily any geodesic, one geodesic had this property. The corollary says in this case we have no anosov hyperbolic behavior of the geodesic flow. Okay, it's an immediate consequence of the theorem. So let me now make the proof of this theorem. Remember, to study the geodesic flow, we remember some important formula about the derivative of the geodesic flow. That derivative has some relationship with the Jacobi field. We consider now that Jacobi field, Jacobi equation. Well, we look in the field decomposition, horizontal and vertical decomposition in the first slide. The derivative of the geodesic flow satisfies this inequality here. The derivative of the geodesic flow in times t in this coordinate, horizontal and vertical, satisfy this important equality. All information about the derivative or the behavior of the derivative of the geodesic flow is only we look for the Jacobi field. All right? So, the formula here, where this moment appear the Jacobi equation. This Jacobi equation is very important to study the behavior of the geodesic flow. Okay, now we introduce some coordinates along the any geodesic to study the behavior of this formula before formula. And this formula says, well, we study the geodesic flow, we look for the curvature. In the curvature, we look for some geodesic in times t. We consider some splitting, some orthogonal parallel space along the geodesic. And this parallel space introduce some coordinate along the geodesic. In this coordinate, the tensor of the curvature is some matrix of the times t. It's a family of matrix or matrix in times t. Okay, so in these ways, we look the orthogonal point in each point theta as Euclidean space. In each point t, the normal point of the derivative of the geodesic is an Euclidean space. In this condition, we look now the stable and unstable bundle given for the some hyperbolic and also flow. And a result of both in the generalized case, but by overlaying the compass case, say that if we look the stable bundle, we look the horizontal space, the stable bundle never intersect the vertical space, and the same way, the unstable bundle never intersect the vertical space. In other words, it's possible to prove, in this case, the stable and unstable bundle is a graph fit for some special function. In fact, it's possible to prove the graph fit of this matrix here, this linear map, this linear map here, is exactly the stable and unstable space. But why is important this matrix here? The more important property of this matrix, that matrix satisfies the Riccati equation in the matrix Riccati equation. All right, here is the tensor of curvature along the geodesic. Okay, well, Green proved that if for any solution of the Riccati equation, when the curvature is bounded below for two constant c, and we have the condition of no conjugacy point, this implies that any solution of the Riccati equation is bounded for the constant c. It's a more important property to me for the proof the result. All right. Remember, giving some point in the stable bundle and another point in the unstable bundle, the derivative satisfies this property here in both points. But by bottom he saw, this point here are never vanished in both cases, stable and unstable. And another important thing, using the graph, the image of the matrix U for the stable and unstable Jacobi field is exactly the derivative of the field along the geodesic. This implies we have this inequality here. All right? Well, using this property of the derivative of the geodesic flow, we look for some special function. It's a function that studies the asymptotic behavior of the Jacobi field in the infinity. The Jacobi field is stable and unstable Jacobi field. Okay? Well, this function using this definition, this formula here, satisfies the stable Jacobi field is bounded for this constant here, depending on the lambda and t, and unstable satisfy this inequality here. In this moment appear again the curvature in this inequality. So this implied by definition of the special function, the function is an bound function, it's an upper bound function. Okay? So now return for the function, look for the function. It's a function where appear the norm or the stable in the stable space. When we can make the derivative of the function, and the derivative of the function satisfies this differential equation. So when we have the derivative of the function appear again for a factor, the function R. Okay, but in this condition, this part of this inequality is bounded for the number 2c. All right, but the proof of the theorem is by contradiction. Suppose now we have lambda is no bigger or equal to minus c. This implies if lambda is less or exponential or minus c, appears some constant here. And this constant here implies for the differential equation the derivative of the function r is bigger than lambda times r. This implies the function r has exponential ground. All right? But the function r is bounded. This implies exponential ground of the function r, but the function r is bounded. It's a contradiction. The proof is very simple, only use real analysis. Real analysis, okay? So, but the proof of the rigidity is it's a little more complicated, but for study the rigidity, suppose that lambda is exactly equal to exponential of minus c. When, in this case, we look for this number here. In this case, this number here is exactly equal to 2c. When we had equality in lambda, appear some important property everybody likes, very likes, or the Lyapunov exponent. When lambda is equal to exponential of minus c, where for every point and for every theta in the unit tangent bundle, the Lyapunov exponent is constant. Does not depend on the point. For every point, it's not oscillated in this case. For every point, not almost every point. For every point, the Lyapunov exponent is constant equal to minus c in the stable space and c in the unstable space. Okay? So let me make a sketch the proof. We thought when lambda is equal to exponential of minus c, this number here is exactly 2c. But this part here is bounded for 2c. This implies this part of this inequality is a non-negative part. But the function is non-negative. Acabó la batería. The function is non-negative. This implies that we have some bounded function, and this function has derivative no. The derivative of the function is non-negative. This implies the function is bounded. The upper bound of the function r. And this function is increasing. This implies the limit when t to infinity, all right, of the function that exists. So we now make some integration in this inequality here. We look that inequality implies this limit here, all right? In other words, appear the norm of the stable and the stable Jacobi field, but using the formula here, everybody now, I think, this implies the Lyapunov exponent is constant equal to c in the stable case and equal to minus c in the stable case, okay? is conclude the proof of this lemma. The Lyapunov exponent does not depend on the point. Well, in this moment, we need find some relationship between the Lyapunov exponent and the curvature. We use now this corollary because the Lyapunov exponent does not depend on the point. This implies this number here, the logit or determinant of the derivative of the geodesic flow, restrict to the stable space, is constant, equal to minus c times the dimension of this space, right? In other words, this number is also constant. But now, by find some relation with the curvature, appears some lemma, it's a Freire lemma, Freire and Mayer lemma in the compass case, but in the complete space is some change in the proof, and it's possible to prove that limit here is equal to another limit, but in this moment appear the trace of the UU operate, okay? The operate or the matrix given the unstable space. Okay, so for the proof, we look for this inequality, for this equality here. In this case, all right, combat. All right, look for this equality and look for this equality here. Well, in this inequality, this part here, it because the derivative or the logarithm or the differential of the unstable, but restricted to the unstable bundle is constant. Well, this inequality here is Cauchy-Schwarz inequality, and in this inequality here we use, look, here appear the square of the trace, but here appear the square in the operator. It's an as possible inequality for symmetric matrix. All right? Look, but we had the operator U satisfy the this. Remember the operator U satisfies this Riccati equation. All right? Well, we can make some integrate in this inequality. We take tres, this inequalities, excuse me. Now make some integration for this inequality for time t. In this moment appear the integral of this operate, the derivative of this operate, plus the integral of the trace of the matrix of curvature. But everybody know this number here is exactly the Ricci curvature or the manifold. Well, in limit here, see because fundamental calculus say integral is exactly trace of the u t minus the trace of the operator u in zero. Well, over t and t go to infinity, remember the operator u is bounded by c. This implies this limit in the first part is equal to 0. In other words, we have, using this Lyse inequality, remember in the first part is equal to time n minus 1, we have now the main equality. This equality says about the average of the rich fall along the geodesy. In other words, for every point, appear some beautiful equality, and that beautiful equality made to remember the Birkhoff ergodic theory. Tá bem, Gugu? The Birkhoff ergodic theory. But for Birkhoff ergodic theory, we need a Ricci curvature is a function of the unit tangent bundle, all right? But it's not necessarily true for non-compact manifold that the Ricci curvature is an integral function, all right? In this moment appear finite volume, because when we had finite volume, a curvature bounded below for some constant, a Guimarães result implies the integral of the Ricci curvature is finite. You know, Florencio Guimarães is aluno do Carmo student. All right? This implies the não fez nada. Cadê o técnico? Foi. Okay. The Guimarães result implied the Ricci curvature is an element of it's an integral function. All right? Well, using now the Birkhoff ergodic theorem, we have the integral of the Ricci curvature is exactly equal to minus c squared. But the curvature is bounded below by minus c squared. This implies the Ricci curvature is exactly equal to minus c squared. And again, where the Ricci curvature is the average of the sectional curvature, we have the curvature exactly equal to minus c squared. In other words, this finishes the proof, because appear the constant where the curvature is exactly equal to minus c. Well, I have 5 minutes, but I finished here. Florencio Guimarães. This result here. Constant or contraction of the flow. This number is curvature is homogeneous space.
Thank you for the introduction. And I would like to say thank you for the organizer for giving me this opportunity to give a talk here in Bahia. Probably the last time I came here was 6 years ago, and I think the university is totally developed a lot. And I would like to say a couple of words about Wellington. 6 years ago, in 2011 and 2012, I was a postdoc at Puki Rio, and so naturally I had several opportunities to went to IMPA to attend some seminars, and there I saw Wellington several times. But at that time I didn't have much opportunity to have conversation with him because my profession is on non-uniformly hyperbolic dynamics in higher dimension, and he's a great mathematician in one-dimensional mathematics. So I got kind of scared to talk with him. 6 years has passed, and now I'm working on non-uniformly hyperbolic dynamical systems for higher dimension. But life is funny because this talk got some influence from Wellington's result. So I think this shows greatness and deepness and broadness of his mathematics. So anyway, let's start. So I'm sorry if this letter is if I'm not sure if this is visible or not, but still I have no way to change it. So let's continue the talk. So I have some manifold, some space, and I am interested in investigating the dynamics on this space by counting the dynamics. And in particular, I'm interested in counting the number of periodic points. So this is a set of periodic points. And so for each period, if you fix a period, then the set of periodic points generally tends to be some discrete set. So you can count the number. So you can, for each n, you have some number, and as a result, you get the sequence of numbers, of periodic points. And my rough question is that I want to know how this sequence varies as n goes to infinity. And one good answer to this question is that if f is hyperbolic, then you can say that the logarithm of this sequence divided by n, if you take the limit, then it's finite. And I say this situation as at most exponential because this shows that the growth of this sequence is smaller than some exponential function. And how can we prove that? If we have hyperbolic dynamics, then we have the decomposition of omega limit set into finitely many number of basic sets. Each basic set is more similar to some horseshoe. Horseshoe, you have a good conjugacy of dynamics. It's conjugate to subsystem of finite type, and for subsystem, you can do the counting of the number of periodic points, and that gives you the upper bound of this sequence. So that's it. So this problem tends to be something serious if you think about some non-uniformly hyperbolic systems. So what about non-hyperbolic case? I have two answers to this question. One is yes, and one is no. And the one is the result by Martens and Domelo and Feinstein. His mathematics. And to talk about that here. And the other one is the one given by Kalosing. So let me give you a couple of words to share the flavor of what's going on in this case. So the first result by Domelo and Feinstein and Martens, Domelo and Feinstein is the following. So they think about interval maps, but this is not a diffeomorphism, but an endomorphism, and they probably has a critical point. But assumes that none of the critical point is flat, in the sense that some of the higher derivatives vanish. Then, in that case, so there are some critical points. So the dynamics, so there are some contracting behavior and some expanding behavior. So if you think about the iteration of this map, then it would be possible that you would observe some neutral behavior. And around there, it may be that if you think about the higher composition, then there could be some higher, very rapid oscillation appears, and that could increase the number of periodic points. But what they did is that by doing some estimation coming from the cross ratio, they proved some inequality that gives you some lower bound of the at a periodic point with higher period, and that gives them some upper bound of the number of periodic point where the period is very high, and as a result, they got some upper bound for the limit soup, and so this means that this sequence grows at more exponentially, smaller than some exponential function. So there's one situation, even if you have no uniform hyperbolicity, you can still have the at most exponential. So that's one situation. And the other situation is a result by closing. Let's think about some open set of diffeomorphism on some surface. And I require that the regularity is greater than or equal to 2. And let's think about some open set of diffeomorphisms, which is a Newhouse region. So what is a Newhouse region? Newhouse region is a set of diffeomorphisms where you have some saddle. Remember that now we are thinking about two-dimensional map. And assume that we have one saddle. So it has one-dimensional stable manifold and a one-dimensional unstable manifold. Then assume that this saddle has some non-trivial homoclinic intersection points. So the set of invariant manifolds exhibits some fractal structure. And assume that the invariant manifold has some homoclinic tangency at some point as well. Then, you know, the tangency point is a kind of fragile object. By doing some perturbation, you can destroy this particular tangency point. But since invariant manifold has some fractal structure, it may be that a small perturbation might create some another extra tangency point. And what Newhouse did is that this is indeed the case, and he managed to prove the existence of some open set of diffeomorphism where a basic set exhibits a robust homoclinic tangency. And Closing did some game, open set, and what he did is around this point of robust homoclinic tangency, what is happening here is that, so there's one expanding direction and there's one contracting direction. And because of the tangency, there's non-trivial recurrence around here. And furthermore, since it is tangent, the existence of tangency means that the expanding direction and the contracting direction is mixed around here. So it may be that we could observe some degenerate behavior around here. We can expect. And what Carlson did is that indeed the case. I mean, by doing some renormalization, he identified some region. Well, now I cannot. That's too much. I mean, I should change the color now. No, it's useless. Okay. So somewhere around here, he took some renormalization, and if he proves that if you look at first return map, then the dynamics has some very neutral behavior, and by adding some extra perturbation, he created a lot of oscillations, with the number of periodic point a lot. And as a result, by doing some Bayes category theorem result argument, he proved that generic map is open set. The map exhibits super exponential growth of number of periodic point. So the limit of logarithm divided by n tends to be infinity. So it means that there would be infinite times where this sequence increases a lot. So I call this situation to be super exponential. Hi. Good question, and I have a good, clear answer to it. I have Japanese writing because this slide is recycled from the another talk. So yeah. And now you revealed my laziness. Thank you for nice question. All right, so I should have hide it now. I should hide it now. All right, so I gave two situation where we have some answer to this question. One comes from the situation where you have critical behavior, and the other one comes from the situation where you have homoclinic tangency. And these two phenomena are kind of related, because if you look at the projection of dynamics which exhibits homoclinic tangency, then you will observe a map which has critical behavior. So in that sense, these two results are kind of similar. And there's another important source of dynamics which generates non-uniformly hyperbolicity. It means dynamics with robust heterodimensional cycles. And as you may know, these dynamics typically leads to the creation of dynamics which exhibits partial hyperbolicity. And it would be interesting what's going to happen in this situation about the growth of number of periodic points. I would like to talk about one result, probably the first result in this direction. That is done by Bonatti and Diaz and Fisher in 2008, 10 years ago. It says that for C1 generic map, if you look at homoclinic class which contains two periodic points with different indices. So this is more or less similar to say that you have some robust heterodimensional cycle. And in that case, they proved that they have super exponential growth of number of periodic points for C1 generic map. And I think this result is interesting, but if you know, in dynamical systems, the C1 topology has some strange behavior. So it would be interesting to ask this question for maps with higher regularity. And that's the beginning of our story. And very recently, we have finished this paper. But before that, last year, I should mention this result. Pierre Berger gave an answer to this direction. What he proved is that he constructed some C-infinity open set of diffeomorphisms where generic diffeomorphism exhibits super exponential growth of number of periodic points, and this is caused by the existence of some partially hyperbolic dynamics. And what he did is that he constructed some partially hyperbolic dynamics in the form of a skew product and looked at its perturbation. So in the base direction, you have partially hyperbolic total automorphism, and in the fiber direction, you have one-dimensional circle map. And what is good for circle map is that for circle maps, we have really strong invariant which detects the non-degenerate behavior. That is rotation number. I mean, if some periodic periodic circle map has irrational rotation number, then it means that by doing perturbation, there's a big chance that you can increase the number of periodic points by adding some perturbation. And what he did is that by using the theory of cocycles of diffeomorphisms and some continuity of rotation number argument, what he proved is that for the perturbation of his dynamics, he can point out, by adding some perturbation, he can create some periodic fiber in which the rotation number is irrational. And by adding perturbation, he increased the number of periodic points as much as he wants. And this is what he did. This result is interesting, but compared to his strategy, I mean, his strategies are really elegant and very beautiful, and I love it. But compared to his result, our result, which I'm going to talk about now, is kind of, pedestrian or primitive or, elementary, in the sense that what we did is just gave some direct calculation of partially hyperbolic dynamics, and in that sense, you could say that's kind of awkward. But still, I inclined to talk about this result because in this result, we did a lot of calculation, and because of that, we can obtain some more information about the dynamics. And because of that, we can I can present you some interesting byproduct of this construction. And that's why I'm talking about the result. How much time do I have? 30 minutes. Okay. I think some of you are already hungry, so I'm hungry actually. Right. Okay. Okay. So, well, let's continue. So, the result is the precise statement of our result is a little bit complicated. So first, I prefer to give you some rough description of what I did. And after that, I want to give some precise statement. So first, let's begin with some rough description. What we did is the following. Think about some diffeomorphisms of some manifolds. I assume that the dimension is greater than or equal to 3, and the regularity here is that greater than or equal to 3. And I allow the case where the regularity is infinity. And I require that F has a robust heterodimensional cycle, and which exhibits some partially hyperbolic splitting, where the dimension of center direction is equal to 1. And there are two results. And the first result is the following. Think about this kind of diffeomorphism and assume that this heterodimensional cycle satisfies some condition about the signature of affine invariant and Schwarzschild derivative. I think you all know what is the Schwarzschild derivative, although some of you might forget the precise formula. Actually, I did forget. I don't know the precise formula, but Schwarzschild derivative is Schwarzschild derivative. It has some quantity which involves some third order derivative. And affine invariant is plays some important role in one-dimensional dynamics. It's the derivative of logarithm of derivatives. So the precise formula, this is I can calculate, and the precise formula is this one. So I require some conditions on these two quantities. Then if your map satisfies the condition which I ask, then you can see that if you look at CR neighborhood of this map, then CR generic diffeomorphisms exhibits super exponential growth of number of periodic points. So in that case, you have super exponential growth. And the second result is the following. Actually, it says that these conditions about the affine invariant and Schwarzschild derivatives are necessary in the following sense. I can give you an example of partially hyperbolic diffeomorphisms, which exhibits, of course, a robust heterodimensional cycle, but which doesn't satisfy the condition which I ask in the first result. And because of that, we can prove that this map C1, C2 robustly at most exponential. So it means that, of course, C2 robustness is C2 robustness implies C3 robustness. So any CR robustness for every R. So the signature is important here. And let me give you one remark, kind of absurd but very important. I mean, just before I mentioned the result about BDP, which says that if you have some map which has a robust heterodimensional cycle, then by doing C1 perturbation, you can make it into super exponential. But this map, although exhibits robust heterodimensional cycle, it cannot be super exponential. So this is an example of diffeomorphism which cannot be C2 super exponential, but can be C1 super exponential. So here's a lesson is that to think about the problem of super exponential growth of number of periodic points, regularity is very important. All right. So from now, I'm talking about these two results. But first, I would like to give you the proof of this second result, because this is much more easier to understand. And after that, I will talk about the first result. How can we construct such an example? So I will construct some partially hyperbolic diffeomorphism, which exhibits robust heterodimensional cycle, of course. And at the same time, we can say something about the number of periodic points. And I construct this map in the way, in the form of a skew product. So in the base direction, you have some hyperbolic behavior. Actually, it's just a hyperbolic total automorphism. And in the fiber direction, you have just a one-dimensional map, say interval or something like that. And what I want to do is to count the number of periodic points. And for that, what I do, for the base direction, the counting of number is just easy. I mean, it's exponential. So we are naturally interested in the behavior in the one-dimensional dynamics. So how can we count it? Here's a there are two important observations. And the first important observation is that take any two orientation preserving convex map on an interval, then the compositions are again convex. Obvious. The second observation is that if you have some convex map on the interval, then if you count the number of fixed points, then it's at most 2. Obvious again, right? So that's a important ingredient of this construction. So let me explain a little the construction. So first, I want to construct some partially hyperbolic dynamics which exhibits robust heterodimensional cycle. For that, I take 3 one-dimensional maps. The first one is some one-dimensional map which exhibits some attractor. Oh, I shouldn't have done it. I mean, one attractor and one repeller here. So this gives you 2 fixed points in 3-dimensional space. And I take two interval map, which whose iterated function system creates a blender. I think most of you, some of you may know that the iterated function system generated by 2 interval maps with contracting maps with overlap gives you blender in the iterated function system. So what I prepare is these 3 interval maps. And here's the important point is that I take these 3 maps to be convex, all convex and orientation preserving. Then what I do is the following. So in the base direction, we have hyperbolic total automorphism. And I take 3 rectangles here. And in rectangle 1, I take F1. I put F1 in the fiber direction. And on R2, I put F2. And on R3, I put F3. So on R1, you have this. You have 2 fixed points with different indices. And on R2 and R3, you have blender. So this, if you take the skew product, then it gives you an example of partially hyperbolic dynamics, which has robust heterodimensional cycle. And I take the extension to the whole space of this map in such a way that for every fiber, you still have convexity. Then, if you look at this exact skew map, you can do the counting of number of periodic points because, so to count the number of periodic points, you only need to pay attention to periodic fiber. And for each periodic fiber, you have convex maps. So the compositions are also convex maps. So in each periodic fiber, you have at most 2 fixed points. Periodic point, I should say. And so in the base direction, you have exponential, and in the fiber direction, you have 2 periodic points, and 2 times at most exponential is at most exponential, if my calculations are not wrong. And so that's why you get at most exponentialness for this particular map. And by doing the construction carefully, you can make it into, you can make this property as robust. How can you do that? I take these skew products in such a way that each fiber is 2 normally hyperbolic. And this guarantees that if you look at the perturbation of this map, each fiber is still manifold. And if the perturbations are small enough, then you can say the closeness of each fiber to the original vertical fiber. And which gives, since the convexity is the information which is determined by C2 information, you can still have the utmost exponentialness of your perturbed map by more or less the same similar argument. I think this is not such a mysterious construction if once you understood. Right? Any questions? So yes, that's it. So this is a construction which I heavily used the information of affine invariant. And by this you can construct this C2 interesting phenomena. And maybe if you look at this construction, you are kind of convinced that you can do the same similar construction by playing with Schwarzschild derivatives. And since you know the positivity of Schwarzschild derivatives imply, if I'm not wrong, the number of fixed points is at most 3, and so you can do the same game with Schwarzschild derivatives. And as a result, I can give you some funny byproduct. I can construct thin infinity diffeomorphism such that this satisfies some obstruction coming from Schwarzschild derivative. And because of that, if you look at C3 small neighborhood of this map, you can say the utmost exponentialness of the number of periodic points. But by doing small perturbation, C2 small perturbation, you can kill the information of Schwarzians, and that gives you super exponential growth of number of periodic points in C2 neighborhood. Right, and I have another 20 minutes, and in 10 minutes, I will explain the precise statement of first result and give some explanation of, I finished my time. Right, and in last 10 minutes, I would say a couple of things about the proof of it. So, well, so I have finished the explanation of second result, and no. I wrote in this way because so that I avoid you can read it precisely, because you know this is something done. So right. So no, this is just to remind you that I have done something. So from now on, I'm going to talk about the first result, and I would like to give precise statement because identify what the signature condition exactly means. All right. So no. So let me give you the precise statement of our result. And for simplicity, I'm going to talk about manifolds of dimension 3. It's really hard to read, but this is 3. I should write here 3. And so let me describe. The result. So I take some diffeomorphism on three-dimensional manifolds where regularity R is greater than or equal to 3, and I allow the case infinity. Give several conditions on this map. The first condition is that I require that there are 2 fixed points. So now the ambient space is three-dimensional space, and I require there are 2 saddles, this guy and this guy. We look at these 2-dimensional manifolds, 2-dimensional unstable manifold. You can define the one-dimensional strong unstable foliation. And in this stable manifold, 2-dimensional stable manifold, you can define the one-dimensional